And then we can have a look at this task number 12, which is, as already said, about distance conversion. And so we have some electric source, and electric source means it's like a Hertzian dipole. It's some electric dipole. And in a certain distance of 3 meters, we have a field strength of this 10 millivolts per meter at a certain frequency of 3 megahertz. And so now what is looked for, what is searched for is what is the field at the distance of 10 meters. And this distance is called R2, and what is the field strength, the electric field strength at the distance of 25 meters. And so what is the practical purpose of such tasks? Why is such distance conversion meaningful, necessary, important? Do you have an idea? Not really? So 3 meters, for example, is a typical measurement distance in anechoic chambers or semi-anechoic chambers. Also 10 meters. 25 meters is not so common. The more common one would be 30 meters then. And there are semi-anechoic chambers with 30 meter measurement distance. They are really, really, really huge. But 30 meters is more an open area test site distance. And so, for example, we only have a small semi-anechoic chamber with 3 meter measurement distance. Do the measurement there in 3 meter distance. But we have a limit that we would like to compare with, and this limit is given for 10 meters. So then we need to convert our field strength measured at 3 meters to a distance of 10 meters. And maybe we would be also interested, okay, what would be the field strength in 25 meter distance when where we have a different victim of disturbance that might be potentially disturbed by this source here. Okay, so let's start with subtask A. So now the question is, how do we do this? What do we need to take care of? What formulas can we use to solve this kind of problem? Who has an idea? And what maybe do we need to calculate first? So one thing that we can calculate from a frequency, and of course we are in an air, free space, vacuum-like environment. So the propagation speed of our electrical field will just be the velocity of light. So velocity of light is approximately, how fast is light? 3 times 10 to the power of 8 meter per second. So, and this velocity of light also corresponds to wavelength times frequency. So if we have this velocity of light, if we have the frequency, we can also calculate lambda, our wavelength. So lambda will be c divided by f. And so if we insert this 3 times 10 to the power of 8 meter per second divided by 3 megahertz, mega is 10 to the power of 6, and hertz is 1 over second. So the seconds will cancel each other, the 3 will cancel each other, 10 to the power of 6 and 8 will give 10 to the power of 2, and these are 100 meters. So we get 100 meters of wavelengths. Okay, so yeah, what would be the next step? What does this, how does this distance conversion depend on wavelengths, or what do we need to take care of? Any ideas? So what would be some very simple approximation or some very simple assumption if we go away from the source? What should happen to the field strength? It should decrease. So we could say something if we know the field strength at one distance. Let's call it E1. Yeah, or no, let's do it like this. So we want to know the distance at the field strength at the distance E2. We know the field strength at the distance E1, and so if so this is the unknown, this is the known one, let's say, but at the end it does not matter. But if we go away from the source, the field strength should get smaller. So how should here be the order of R1 and R2 so that in a greater distance the field strength gets smaller? R1 by R2, exactly. Yeah. So if this is a small distance, we have the high field strength. If this is a large distance, we get the small field strength. So and this formula is valid in the far field. So this would be far field conversion. Because, as we discussed, in the far field, we have the same ratio between electric field and magnetic field, and the same power is, we have not the same ratio. We have a constant ratio between the electric field and the magnetic field, and this ratio between the electric field and the magnetic field we call, for example, eta. And so what is the unit of this eta? What is the unit of the electric field strength? Volts per meter. What is the unit of the magnetic field strength? Ampere per meter. And so the meters will cancel each other. We will get volt per ampere, and this is ohm, right? And so that's why we call this ratio wave impedance, intrinsic wave impedance, free space wave impedance, and for a far field, it's 377 ohm. So here this eta is approximately, not exactly, approximately 377 ohm. And so we have a constant ratio between electric and magnetic field, and so we have kind of the same energy in the electric field component and the magnetic field component. And imagine you have a source. Yeah, so remember my analogon where I said, okay, this is the dipole, this is the source, and it will radiate waves that are spherical waves, where the wavefront is a sphere. And so the energy or the power that is radiated is distributed on the surface of a sphere. There is some directivity, but okay. And so if we are in the far field, and if we double the distance, so if we go to twice the distance, what happens to the surface area of the sphere? No, if we double the distance, the sphere gets larger. Yeah, so I have a certain distance, and I imagine a sphere going around here. And so now the sphere has a certain surface area, and power radiated by the source divided by the surface area gives power flux density. And so if we double the distance, what happens to the surface of the sphere? No, it should be 4 times as large. It should be 4 times as large. Yeah? But if we double the distance, the area gets 4 times larger. So the power flux density, this goes down by a factor of 4. And so because power flux density, what we call S, is in the simplest case, let's say E times H. Yeah, if we don't take...
Maybe they don't see the screen.
Maybe they don't see the screen, exactly. Very good point. So if we calculate this power flux density, E times H, so this goes down by a factor of 4, because this goes down by a factor of 2, because this also goes down by a factor of 2. And this totally makes sense. Okay, so this is the formula valid in the far field. There is a different formula that is valid for the near field. And for the near field, we have something similar.
It should be
Yeah, so I will write down the very same formula. So E2 divided by E1 is R1 divided by R2. And yeah, so then there is a certain factor. And so the idea is that it's squared. We will think about this in a second. So, and so in the near field, we also have a similar formula for the magnetic field. And I will also write it like this. H2 divided by H1 is R1 divided by R2. And so there is also some exponent here. And so now the question is, what are these exponents here? And I will delete this exponent here. And I would propose the exponent here is 3 and the exponent here is 2. And why is it like this? Or why must it be like this? Because we have some electric source. And what does electric source mean? It's some electric dipole, some Hertzian dipole. And so it means that if we go close to the source, we have much more electric field than magnetic field. So imagine, yeah, so we have a certain field strength at a certain distance, and now this R2 here is much smaller than R1. We go closer. So we have something divided by something small, so it gets large. And if we have it to the power of 3, it gets larger. Then whatever we have here, that is increases by the power of 2. And so for the electric dipole, these are the formulas for the near field. For the electric dipole in the near field, this is power of 3, this is a power of 2. If we would have a magnetic source, yeah, so let me just use a different color. If we would have a magnetic dipole, then this would be a factor of 2 instead, and this would be a factor of, or an exponent of 3 instead. Because close to the magnetic dipole, we need more magnetic field. And close to the electric dipole, we need more electric field. That's why these powers. Okay, and so then we can say if we are close to, later. So now the question is, and that's probably the next important question now, what is the border between far field and near field? Where does the far field end? Or where does the near field end? Where does the far field begin? Any ideas for this? What is the transition distance, or it's also sometimes called, let's say, magic distance between near field and far field? Yeah, and this must be the case for a certain frequency. Yeah, this is 50 Hertz, and for 50 Hertz, I think this is just the wavelength of 6,000 kilometers. It's not yet the transition distance, but this transition distance, of course, depends on the wavelength. And yeah, so if we go back to the lecture slides, the answer is, of course, given there. Yeah, so that's the idea of the distance conversion, and so our solution, and this is this transition distance. It's just 1 over k, or 1 over the wave number, because the wave number is what is inside there of these exponential functions. Yeah, if you remember, these were formulas that we have written down for these dipoles. This is for the magnetic dipole, but for the electric dipole it looks similar. And so there we have e to j kr, and we have 1 over kr and 1 over kr squared. This is in the far field, yeah, and in the near field you have this 1 over kr to the power of 2 and 3. And so if these factors get smaller or larger than 1, then something happens. So this happens if k times r equals 1. Yeah? And so that's why the transition distance is just 1 over k. And 1 over k is the same as lambda divided by 2p. So this is our transition distance that we need. R0 is 1 over k is lambda divided by 2p. And so in this case we can calculate this, of course. 100 divided by 2p is approximately something like 60 meters, right? Because p is 3, 2 times p is 6, 100 divided by 6 is something like 16. And of course, p is a little larger than 3, so we get something slightly smaller than 16. And so we can use Octave and we can do this calculation in Octave. And hopefully now it won't crash. So I will insert these values. C is 3 times 10 to the power of 8. Our frequency was 3 megahertz, and this lambda was c divided by f. This should be our 100 meters, and that's right. And so then the transition distance is the lambda divided by 2 and divided by p. And so we get 15.9 meter. Okay, so this 15.9 meter, in this case, this is the transition distance between the far field and the near field. So far field means our distance is larger than this transition distance, and near field means our distance is smaller than this transition distance. And so in the far field, we had this 377 ohm of field impedance, and in the near field, if we use this formula here once again, yeah, so then we get something that the free space, or that the, let's call this eta 0. So this is the one that we have in the far field. And so in the near field, we could now, in this general formula, insert this dependency here and cancel some stuff. But at the end, we could also just say that in the electric, or in the near field of this electric source, we have more electric field and less magnetic field. So if we have more magnetic field, less magnetic field, then we get a high impedance field. So the closer we go to the source, the higher will be the wave impedance. So we get eta 0, and if it needs to get larger, if we go closer to the source, so how must be the ratio between the distance and this transition distance? What must be in the numerator? What must be in the denominator? And so if you think about this for a second, it must be like this, right? If this distance is smaller than the transition distance, something divided by something smaller is getting large, and so we get a high impedance field. And so this means our near field of the electric source is a high impedance field. High impedance field. And if we would have, once again, our magnetic source, so for the magnetic source, it would be exactly the opposite, R divided by R0. And so here, if you go closer to the source, then also the field impedance gets smaller. And so for the magnetic dipole, we get a low impedance field. And this is later on very important for shielding, for example, because high impedance field is easy to shield because you get a large reflection coefficient between, let's say, air and metal. If you have a metal shield, if you have a metal wall, the wave impedance in metal is very small. So if you come from a far field or from a high impedance field, you will get a large reflection. Most of the wave will be reflected back, no problem. But if you have a low impedance field, if you have a magnetic source, magnetic sources are difficult to shield because you have low field impedance outside of the shield in the air, you have low wave impedance inside metal, so you don't get any reflection. So you need to rely on absorption, which is difficult to achieve because you need a very thick shield later on. And this is, we will come back to this, remember this when we talk about shielding. Okay, so now coming back to subtask A, what conversion formula do we need to use here? The near field one, because this point is obviously in the near field and this point is also obviously in the near field. So we need to use this conversion formula for the near field with this exponent of 3. So yeah, I can just insert the values. So our E2 we get from E1 if I move this to the other side and then multiply it with R1 divided by R2 and this to the power of 3. And so it's 10 millivolt per meter multiplied with R1 is 3 meter, this is 10 meter, and this to the power of 3. Yeah, and so we have a fraction here that is smaller than 1, which also makes sense because in greater distance our field strength should get smaller. Okay, the numerical calculation I will once again do in Octave and hope that it won't crash this time. So we can say R1 is 3 meter, R2 is 10 meter, E1 is 10 millivolts per meter, so I will write it like this, really in milli. And so E2 is E1 multiplied with R1 divided by R2, and this to the power of 3. And so we get something smaller. If I take this and maybe multiply it with 10 to the power of 6, then we get 270 microvolts per meter. Okay, this is the field strength at this distance. Then we can continue with subtask B. And for subtask B, now we have a distance of 25 meter. And 25 meter is, it's already in the far field. So, but how do we now convert into far field? Because this is in the far field. The other 2 points that we have, 3 meter and 10 meter, they are in the near field. So what maybe intermediate step do we need to do? Because this conversion rule only applies for the far field, this conversion rule only applies for the near field. But let's say there is one point that belongs to the near field and to the far field at the same time. And this is R0, R0, this transition distance. So what we need to do at B is, at first we need to convert, I don't know, from the 3 meter or from the 10 meter, from what we know, what is in the near field to the transition distance using this formula. And then from the transition distance to the far field using this formula. Okay, so I will, I don't have enough space here, so I will write this on the next page. So we will say, okay, E0, our field at the transition distance, we will get from the field that we know, E1, and then we can say, okay, it will be R1 divided by R0 to the power of 3. So this will be our near field conversion. This is once again near field. And so we can insert some values there, and then we get E0, and so then we can calculate E3 from E0, and R0 divided by R3, and there we just have the exponent of 1, because this will be the far field conversion. Okay, and so now we can just insert the values here. We still have 10 millivolts per meter. R1 is 3 meter. The transition distance is 15.9 meter. And here we have this exponent of 3. And then whatever we get, we need to multiply with 15.9 meter divided by 25 meter. Our distance are 3, and here we just have an exponent of 1. That, of course, I do not really need to write, but to show the difference, I will write it in this case. Okay, so now I will go back to Octave, adjust the screen size here a little bit, and we can calculate E0 or E0, the electric field strength at the transition distance from E1 multiplied with R1 divided by R0. I should have just copied the formula from above, yeah, but it's the same formula. And so we get something like 66.9 microvolts per meter, I think. Yeah, so 66.9 microvolts per meter. And so this is also what we will then insert here. And do the final conversion in the far field. So E3 we get from E0 multiplied with R0 divided by R3. And I think we don't have R3 yet, so MATLAB will, and okay, and I also forgot something there. So R3 is 25 meter, and there's some underscore is missing. And so it should get smaller, of course, now. And so we get 32.6 microvolts per meter. And this is the electric field strength in 25 meter distance. And so, yeah, this is the full solution, including some explanation of what happens here in the background for this distance conversion task. Which questions do you have? You are looking very skeptical.
I have one question.
You have one question.
15.9 is the reference for the minimum. That up to that distance we have far field.
Exactly. Up to this distance we have near field, and above this distance we have far field.
No.
And so this is what is called transition distance, or border between near field and far field, or sometimes it's, I don't know, called magic distance, something like this. Okay, more questions?
Can we move to the second page?
Sure. Yeah, so hello back to the 4 people watching on Twitch. If you have some questions there, feel free to write them into the chat. I should also be able to read this.
Here the power is 1, right? R0 divided by R3 is power 1.
Yeah, this is a power of 1, because this is far field. This is the far field conversion, this is the near field conversion, and this is what we have discussed before, that in the near field you have these exponents of 2 and 3 depending of if it's a magnetic source or electric source, and in the far field you just have an exponent of 1.